Thank you for the opportunity to talk to you. The subject will be, as announced by the chairman, Metabolomics of Inborn Errors of Metabolism, and we'll focus on how we can use it to get informed on genetically predisposed allostasis. The work was done at the National Metabolomics platform, which is located at the Northwest University in Potchefstroom in South Africa, and the clinical material, which was urine samples at the time of diagnosis of the children, and then after treatment, as well as blood, which was used for the genotyping, came from the diagnostic laboratory that is also at the university and actually performs a diagnostic service for South Africa on the inherited disorders. Now I will briefly say what is IVA, the metabolomics workflow that we followed, the global metabolite profile in the disease, phenotype and genotype variability, a model on allostasis, and some conclusions and recommendations. So what is isovaleric acidemia? Very simple. It's one of the first organic acids that have been described, and it is a defect in the catabolism of leucine, the amino acid, and it is due to a genetic disorder in isovaleric-CoA dehydrogenase enzyme, and the diagnostic metabolites for the disease is 3-hydroxyisovaleric acid and the detoxification substance in isovaleric glycine. Now, from a genetic point of view, it is one disease. It is in the IVD gene, but in fact, from the literature, we know that there are at least 50 different mutations in this disease, in this gene, and all of them causing the same disease, basically the same disease. These mutations are splice mutations, approximately 35 of them, non-splice mutations, nonsense mutations, splice mutations, 9 of them, insertions, 5 of them, and then in our own case, we studied 10 of these patients. It appeared they all had the same genetic mutation, although the 10 cases came from 7 apparently totally unrelated families. It is a missense mutation in exon 4, caused a substitution for arginine for glycine, and reduced the enzyme activity to very low, at least below 5%. So it is a very clear defect in the enzyme due to that mutation. Now the workflow that we followed is very simple, well known. Of course, you start with a good description of your cases, which were the patients and after treatment, and then obligate heterozygotes, parents of the patients, and controls for the patients, infant controls and adult controls. Doing a PCA, we first extracted, of course, the organic acids and identified them through AMDIS and a custom-made library, and we found in total more than about 250 different metabolites. There is the control group and the 5 different groups there. And then after some data reduction, because there's a lot of zeros in, we have the final matrix approximately 50-55 variables for these cases. And if you do then a PCA or a concat that we used, is basically also PCA, there was a very clear natural separation between the controls, infant controls, and the patients before treatment and after treatment, and between the adult controls and the carriers. And the question then, of course, is what caused these differences, and then we did that. Not going in all the detail because it is a lot of work. We compared the effect size, which is basically a fold change. Oh dear. This is now at the end of its life. It is a fold change, and the PLSDA, the top variables there, the PCA top variables, low p-value, and we compare it for the different experimental groups, and I rank them according to interpretation, biological, biochemical interpretation. First of all, important ones are the detoxification markers, of which the one that I already mentioned in isovaleric glycine, dominant marker, but also very low concentrations that you can see in the other two. Then there are the markers which I call secondary metabolites, of which in 3-hydroxyisovaleric acid, which is also a diagnostic one. Oh, that's fine. Let's see if this one's, oh yes, it's good. That is also very high concentration and is also a diagnostic marker that was there. And then there are a couple of markers that were identified who were related to the clinical characteristics of this disease. Now, the question is, how do you interpret these so-called markers or, in the metabolism? And for that purpose, we developed a metabolic pathway, or complex metabolic pathway, based on our basic experience in metabolic disorders in the PLEAM lab. And it turned out to be quite a complex set of reactions. And I've indicated there is the pathway from leucine, and the defect is there. It is a mitochondrial defect. And the accumulation of isovaleric CoA caused then several reactions that rose due to that high concentration. 4 of these metabolites are detoxification substances, and the other are then secondary metabolites. And as you can see, it involves not only the mitochondria, where the disease is, but also the urea cycle, peroxisomes, and the endoplasmic reticulum. So it is quite a comprehensive effect of this single gene defect. A very important characteristic of this disorder, as in many of inherited diseases, is the variability from a clinical and genetic, as I just described, point of view. Now, from a clinical point of view, that, as I said, is the most important marker. And if you look at our small cohort of 10 cases, they phenotypically range from mild to severe, there, which is largely linked to the concentration of the detoxifying substance. Now, a very interesting point is the very first one that we got, that one, which was referred to as baby was critically ill, and the sample arrived at the laboratory, and before we could even finish the diagnostic procedures, the child died. So it is an indication of a very severe disease if not get the good attention. And 18 months later, we got a sample from the same family, and another boy was born. They immediately said the sample, we diagnosed it, and it was again exactly the same disease. Now, 2 decades later, there was an individual, yes, our group in the lab, was individual apparently healthy because he was treated very soon after the diagnosis, which also indicates the peculiar and hopeful situation with regard to this disorder. But this whole situation and the metabolomics led us to formulate a hypothesis, and that is that we think that in the acute episodes of the neonatal period and in the early infant stage, there will be indications of the perturbation of homeostasis, generally known as allostasis. And of course, the allostasis may develop into allostatic load, and the allostatic load has potential fatal consequences for this disease, as I've just indicated in that one case. Now, to do that, we again look to the original markers that we had, and we use a different method, which is not going to describe in detail, where each of the 200 plus metabolites are used for a classification purpose, either as a patient or a control. And you can see the yellow ones are the detoxification ones, with, of course, the best classifiers. But there were also the red ones were also closely related to what we say intermediate metabolism. So it indicates that apart from the detoxified markers, there are other information as well. So we did two analyses, PCA with all the metabolites that we measured, and you can see there's a clear separation between a PCA separation, natural separation between the patients and the controls. And if you take out only those 10 or so detoxification markers and do it again, there's again a separation, natural separation. There is the controls there and there is the patients, but of course the separation is less clear, but it indicates that there are information there. We followed the same route, doing exactly the same procedures as the previous one, and indeed we found lactic acid, which is very dominant in these patients, and that clearly relates to energy crisis. I will come back to that now. And then there are further indicators of an energy crisis. There are good examples of ketosis present in them. Other examples related to lipid metabolism or catabolism, and then the 3-hydroxyisovaleric acid, which I already mentioned, and the last one I will come back later. So indeed there are, apart from the detoxification markers that we've shown before, there are this whole group. Now, how do you interpret that? We then went to the literature and made an extensive investigation of what happens shortly after birth, because that is the stage when we know if they are untreated that it will be the fatal stage. So, and we used basically the basic model that we developed, what came from the work of David Sabatini, which I think most of you well know. His work on knockout neonatal mice. So immediately after birth, it is a well-known phenomenon. Immediately after birth, there is the glucose, more or less, not absolute concentration, the glucose there. There is this decline in the glucose. That is a phenomenon which happened all of us shortly after birth, and that is then corrected by the ADP system, and later on the mTOR is activated as well, and autophagy occurs, which mobilize the amino acids which are used further for energy, and then in the later phases the SIRT system activates the normal process, and we have homeostasis and normal development. That is the normal process. And our question is, what would happen in the case of these patients? So we looked again at the model, and first, in the first part, the red part is now in the patients, more or less the same, high lactate, ketosis, and it's clear that you have there a kind of Warburg effect that you also see in cancer cells in the very early phase. And then there's the first point where there apparently occurs a problem from experimental studies with mice, nutritional studies. It is clear that high concentrations of 3-hydroxyisovaleric acid inhibits the mTOR system, which means there cannot be autophagy, and it stimulates growth, which requires energy, which is not present. And then in the next phase is also very well-known phenomenon with the SIRTs, that they can be acylated. There are various ways that they can acylate it, and then also not restoration of the energy. So this whole process then would give rise to this allostatic process, which might culminate in severe hypoglycemia, coma, and even death. Now, when you treat the patients with for example, carnitine, that is removed, and then you will have normal development as we saw in that man. So, in conclusion then, the untargeted metabolomics investigation of IVA provided a functional readout of the metabolic state that prevails in this disease, and secondly, that it indicates the system-related perturbations in the global metabolite profile. The diagnostic biomarkers is predominantly the detoxification markers, And then I think this the important new thing from this paper, some non-diagnostic biomarkers are indicators of perturbed homeostasis in these patients, acutely ill patients, reflecting a possible state of genetically predisposed allostasis, which might develop into an allostatic load with potential fatal consequences. And the recommendation is because it is unique, and every of these individuals, a multidisciplinary approach with clinicians and metabolomics and genomics would be advisable to assist, give the best possible assistance towards those affected individuals. I acknowledge the lab where it was done and the funds that we gave, and thank you for your attention.
So on one slide you showed that with an increase of succinate, this leads to a reversal of the Warburg effect. Can you comment on this?
Yeah, it's a very interesting phenomenon. The Warburg effect typically occurs when there is an kind of energy crisis, which is the best described in the cancer cells. The cancer cells go to the anaerobic state, and the aerobic state works differently. Now, this is virtually the same it clearly indicated, same in the very initial phases after birth. After birth, the umbilical cord is cut, and we go into a severe energy crisis. And the only way to survive this energy crisis is to get alternative source of energy, and that comes from the amino acids. But the formation of lactate from the glucose that was there is high, but that changed later on. So the Warburg effect is typical in the first, let's say, hours after birth. But in this case, because there is no restoration of the formation of amino acids, you see that even a month or so after birth, you still have that very high lactate, which is indication that the glycolysis is a major source of energy to these patients. That's more or less the mainline thinking of the model.
So you mean then the increase of succinate leads to an increase in general TCA activity, which indicates a decrease in aerobic glycolysis? I'm just asking because, or maybe it's in Inborn's different, but there was last year, I think, a publication in Nature by Tannehill, and they showed actually under inflammatory activated macrophages, the succinate level is also increasing, and this leads to an inhibition of prolyl hydroxylase, which then stabilizes HIF1 again. And then due to the stabilization of HIF1, this leads to a pseudo-aerobic, a pseudo-hypoxic state, which then introduces actually aerobic glycolysis or the Warburg effect with high levels of succinate. But maybe this is then special due to inflammation or so.
Well, I'm struck on the extreme complexity and interesting complexity of the regulatory mechanisms in various conditions related to an energy crisis, or even in aging, where we go talk aging, you see more or less again this D-rate regulation. So I'd like to have that paper to look at it and the reference to look at it.